We all know web security feels like hitting a massive, constantly shifting target. You put your code out there, and the moment it hits production, it feels like this whole new array of exploits just pops up. It can feel fundamentally overwhelming.
It's the anxiety of the modern internet, isn't it? You see these big companies, they announce massive data breaches almost weekly, and you think, well, if they can't handle it, how can I?
Right.
But here's the cool breakthrough we found digging into these sources. That chaos, it's mostly an illusion.
Illusion, how so?
The number of, fundamental web vulnerabilities is surprisingly small, and critically, they don't really change much year to year.
So the mission isn't to chase every single headline about some new flaw. It's to identify that small, unchanging set of core threats and just learn the practical defenses. It's about being disciplined, not some kind of genius.
Exactly. We are essentially looking at the difference between, say, fixing a leaky sink once and mopping the floor every single time it overflows. We're here to find the permanent leaks.
Okay, let's unpack this. We're going to start by confronting the reality of the threat landscape. Because before we can build any kind of defense, we need to know just how low the barrier to entry is for the people trying to break in.
The first step in defense is always understanding your adversary. And when we talk about hacking, we need to distinguish between a vulnerability,
which is the flaw in the code itself.
The flaw in the code, and an exploit, which is the piece of code that actually shows you how to take advantage of that flaw.
And the sources paint a really clear picture of the economy around these exploits. You have the white hats, the researchers fixing things, but then you've got the black hats who are just hoarding and selling them on the dark web.
They're financially motivated. They have to stay ahead. And that's where the term zero-day exploit comes from. It's a flaw the vendor has had literally 0 days to patch.
And once it's found, the exploit is weaponized.
Instantly. It gets integrated into command line tools, sold alongside stolen credentials, compromised servers, the whole package.
That speed is staggering. But here's the truly eye-opening part. For anyone who thinks hacking requires some special genius, the tools are not only powerful, they're free and easy. You can just go and download Kali Linux. It's a free version of Linux that comes pre-installed with, over 600 security and hacking tools?
It's an instant toolkit.
It is. It just dramatically lowers the learning curve.
And once you have Kali running, you open up Metasploit, which is described as the most popular tool for this.
For testing and exploiting vulnerabilities, yeah.
I do love that the source image mentions you need sufficient ASCII art cows to operate it, which makes it sound a little less terrifying than it is.
The ASCII art is a nice touch, but aesthetics aside, the power of a tool like that is just undeniable.
And you don't need to be an expert to use it.
No. Running a utility like a ROMAP on a target site, it scans a list of URLs for known flaws. It requires no particular expertise to set up, but it is phenomenally good at finding those common vulnerabilities.
That's the kicker, isn't it? The barrier to entry for the attacker is just extremely low.
It is. You don't need a PhD. You need to install a free OS and run a preloaded script.
Which means relying on security through obscurity is completely dead. Our defense can't be based on the hope that an attacker won't find the tools.
It has to be based on the certainty that we've patched the fundamental flaws the tools are looking for.
Exactly. Systematically.
Okay, so now that we've established the threat is very accessible, let's zoom out a bit. Let's look at the infrastructure it's attacking, the components of the internet itself.
Right, so if you look at the basic plumbing, we're relying on these foundational protocols. When you send a message, TCP, the transmission control protocol, handles the reliable data exchange.
Splitting messages into packets, reassembling them, all that stuff.
Yeah, using sequence numbers. And then on top of that, you have HTTP, the Hypertext Transfer Protocol, which is how web servers transport pages.
And because no one wants to remember long IP addresses, we have DNS, the domain name system, to translate something human-readable like example.com into the right numbers.
This design is what makes the web work, but it also creates, well, inherent security compromises. Take cookies, for example.
Right.
HTTP is fundamentally stateless. It doesn't remember you from one page load to the next.
So cookies were introduced as, like, a necessary evil to create stateful connection.
To create an HTTP session, yeah. To track the user. And because that cookie contains all the session info proof you are who you say you are, it immediately becomes a juicy target for hackers.
If it's stolen or forged, the attacker can just impersonate you.
Hello, session hijacking.
And it's not just the core functions that have risks. I mean, even obscure protocol methods that developers barely think about, like the trace method.
The trace method, right. It's designed to echo back a request, which
Yeah.
seems useful for debugging,
Yeah.
but the recommendation is to just turn it off in your web servers.
Why is that?
Because the source material points out that trace can act as the security hole. It can potentially let malicious JavaScript access cookies that were specifically marked as inaccessible to JavaScript.
So it bypasses the HTTP-only defense.
It can, yeah.
That's a fascinating detail because it shows a threat can exist where you thought you already had a perimeter. Okay, so let's jump up the stack. How much better is the browser at locking things down?
Well, a browser security model is your first line of defense on the client side. It restricts JavaScript to a sandbox.
And that sandbox is generally pretty successful, right?
It is. It means malicious JavaScript on a page can't just read arbitrary system memory or access your local disk or start new processes.
But the danger zone is that JavaScript can still read and manipulate the document object model.
The structure of the page, exactly. And it can make HTTP calls on the user's behalf.
Which is why cross-site scripting, or XSS, is still so incredibly dangerous.
Because by injecting malicious JavaScript, attackers aren't breaking out of the sandbox. They're just manipulating what's inside it. They can steal your credentials as you type them.
Okay, so moving back to the server and the data, we have static resources,
Like images or the original Space Jam website.
right? Stuff that's returned unaltered. And then dynamic resources, where the server is actually executing code using templates and databases.
And those databases? That's the holy grail for attackers.
That's where all the good stuff is.
Absolutely. And when you look at data storage, you're primarily dealing with two types. You've got relational databases, usually running SQL-structured query language, highly transactional, very consistent,
And then you have NoSQL.
which is often schemaless. It sacrifices that strict data integrity for massive scale.
When you're assessing the risk here, it goes beyond just the architecture choice. With rigid SQL, an attacker knows exactly what format to try and break.
The injection points are predictable, yeah.
Yeah.
But the schemaless nature of NoSQL brings its own challenges. Input validation gets trickier because the expected schema is more flexible, or it might not even exist.
So that can open up new kinds of risks, like JSON injection.
Exactly. The key point is that no matter which one you choose, both are vulnerable to injection attacks if you don't maintain discipline.
Which leads us to the big reality check for every developer: third-party code. We might focus on our own code, but what a small minority of the running code is actually written by our team. We rely so heavily on CMSs, libraries, CDNs.
And even though experts write this third-party code, its ubiquity makes it the biggest target. An attacker doesn't need to find some unique flaw on your site.
They just need to Google WordPress vulnerability.
And if you haven't patched your system, your site is exposed. Infrequently patched legacy systems are a huge and often self-inflicted liability.
So given how easy the tools are, how many weaknesses there are in the architecture, relying on tech alone is not enough.
Not even close.
Which is why we need to move to the rigorous defense side of this, the process, the software development lifecycle, the SDLC.
Right. Security is not a feature you can just bolt on right before you launch. It has to be an iterative process, integrated through the whole lifecycle.
And the sources really highlight that most vulnerabilities creep in from, what, lack of attention?
Lack of attention, developer shortcuts under pressure, general technical debt. It's the small things.
And that discipline has to start the moment code is written, using source control like Git.
It sounds so basic, but Git isn't just for backing up code. It's for tracking every single change, providing that crucial audit trail you need to diagnose and fix a security issue later.
And tying into source control is a great human defense. The 4 eyes principle.
I love this one. It just means requiring 2 separate people to see and approve every code change before it's released.
It dramatically reduces the chance of a simple but exploitable mistake getting through.
It's human nature, right? You're racing a deadline, you overlook one little input validation.
And suddenly you have a massive vulnerability. Having a second person review the security logic, not just the formatting, saves you from yourself.
Absolutely. Though if your team is anything like most, those 4 eyes will frequently be needed to resolve merge conflicts because, Dave decided to refactor the whitespace in 1,000 files.
We all know a Dave.
We do. But despite that pain, the code review process is vital.
And beyond manual review, you need automated testing. Unit tests.
Small scripts that verify specific bits of code. And the rule here is simple. If you find a bug, you write a unit test to prevent it from ever happening again, then you fix the bug.
That's true prevention.
It is. And as you move toward deployment, your testing environments, your staging, your QA, they must be fully segregated from the production network.
Physically separate.
Yes.
Hmm.
An attacker should never be able to pivot from an insecure QA server into your live production system. It's like keeping the rehearsal stage totally separate from the main show.
And here is a crucial oversight the sources highlight as the cause of, numerous high-profile data leaks.
Yeah.
Test data.
Oh, this is a huge one.
You copy production data into a test environment for realism, which lots of companies do.
You have to.
But you must scrub the sensitive information. Passwords, credit card details, PII. If that unscrubbed data is living on some insecure, forgotten test server, it is a catastrophic liability.
That's a scenario where rigor in the SDLC just pays immediate dividends. And when it comes to the final release, the process itself has to be three things: reliable, reproducible, and most critically, revertible.
Okay, let's break that down. Reliable means using checksums, right? To guarantee the code you're deploying is the code that was approved.
Yep. No corruption, no accidental substitutions. Reproducibility means the process is automated. You use scripts to eliminate human error.
And revertibility. That's the emergency escape hatch.
It is, because things always go wrong. Being able to seamlessly roll back to a prior, known secure version is vital. The sources describe a partial rollback as a disaster waiting to happen.
Where you only revert some parts but not others.
Exactly, because it often leaves behind insecure configurations or mismatched dependencies. It's a mess.
And speaking of dependencies, we mentioned that small minority of code your team actually writes.
Which means you're running this huge supply chain of third-party libraries.
And you have to stay ahead of security advisories for every single piece of it and patch them immediately.
Even if it's outside your normal release cycle. If WordPress or your Node runtime announces a critical flaw, you can't just wait 2 weeks for the next sprint.
The developer's job is not just coding features, it's managing risk.
Fundamentally.
That's why we need to dive deeper into one of the nastiest threats identified in these sources. The one that exploits all these weak points? Injection attacks.
Injection attacks are the straightforward definition of what happens when that rigor fails. The attacker injects external code into your application, usually through user input.
To try and take control or read sensitive data.
Exactly. It usually happens where your application interfaces with the database or maybe the operating system shell.
And SQL injection is the poster child here.
Classic example. It targets structured query language, which is how we manage relational databases. Hackers go after SQL because that's where the sensitive data is: user accounts, orders, payment details.
And the vulnerability happens when developers insecurely construct their SQL statements, right?
By mixing raw user input directly into the SQL command string. So if the application is expecting, say, a username, but it gets malicious SQL code instead.
And that lets the hacker run their own unauthorized actions. The example in the sources is just chilling. If you don't correctly escape the input, a simple login query might be interpreted by the database as a command to delete every single user.
Something like delete from users, where email equals billy@gmail.com, and that's not theoretical. That is how some of the largest data breaches in history have happened.
So what's the mitigation?
Thankfully, it's well-defined and it's absolute. Developers must use parameterized statements or leverage something called an object relational mapper, an ORM.
And the reason those work so well is because they force the user input to be treated strictly as data, never as executable code.
They create a clean separation of command and data. It fundamentally neuters the injection attempt before it can even touch the database engine.
That separation, that's what discipline looks like in practice.
It is.
So what does this all mean? The sources are clear. Securing your site is not about genius. It's about discipline. Across the entire software development lifecycle,
Right.
it means learning that relatively small list of core threats and implementing these rigorous processes: code review, testing, deployment.
And if we connect this back to the bigger picture, remember that the internet evolved so rapidly and frankly so haphazardly. Features were always prioritized over security in the early days.
And we're still paying for that.
We are. That legacy means we are still fixing fundamental issues that were first introduced a decade ago. It raises a really important question for you, as someone relying on these services.
What's that?
If the greatest risks come from these old foundational systems, which foundational layer of the internet are we still operating under an assumption of good faith, even though we know better? The challenge isn't the new attacks. It's the security issues inherent in the protocols we trust completely every single day.
Don't panic, but get disciplined. That's all the time we have for this deep dive.